Welcome, Geometry Honors. So 12.7, we're going to be exploring similarity with solids. And something that's kind of interesting about similar shapes is if you've got any two cubes, they're going to be similar. If they're a cube, they are similar. And so what that means is if you compare two corresponding sides, and then compare that to other two corresponding sides, they're going to be the same ratio. So also any two spheres are similar as well. But that's not the case with other shapes. So example 1 says tell whether cylinder P is similar to either or both of the other two cylinders given. So we've got measures of radius on each of the cylinder. We also have measures of the height for each of the cylinders. So those are the two measurements that we can compare to see if we've got similar figures. So what I'm kind of noticing is, so there's a few ways to do this. One way to do this is to find out what the ratio is between radius and height on cylinder P, and that ratio should be equivalent to any similar shapes. Another way to do this is to say, well, I'm going to compare the radiuses on each one and then see if that compares to the same ratio with the heights, and see if it works out that way. So there's two ways to go about this. The first way I thought about going about it was comparing radius to height and getting that ratio. So this is cylinder P. So radius to height is 3 to 5. And then on A, it was 9 to 15. And on B, the radius to height was 9 to 10. And then, so at first glance, it looks like none of these are similar, but when you reduce those fractions down, you get 3/5 is equal to 3/5 here. So it turns out that cylinder P and cylinder A are similar, but 9/10 doesn't reduce, so it wasn't equal to 9/10. So it turns out that P is similar to A. And again, you could have also done it by comparing, which is probably the more appropriate way to do it, is to compare radiuses to radiuses, heights to heights. So radius to radius, you get 3/9. And then from height to height, you get 5/15. And then if those ratios are equal, then you know they're similar. And it turns out they are. It's 1/3. 1/3. So that's a way to know cylinder P and A are similar. And then if you do B, you'll get, what will it be here? 3 to 9 again, but then it's 5 to 10. And you quickly see 1/3 does not equal 1/2. So the ratio of those corresponding sides are not the same. So again, P is similar to A. So similar figures, we've done these in the past, it's just now they're three-dimensional. So this is where it gets interesting, is the similar solids theorem. If two similar solids have a scale factor of A to B, then their corresponding areas, or surface areas, have a ratio of A squared to B squared, and their corresponding volumes have a ratio of A cubed to B cubed. So I think we've done this in the past, comparing area and versus lengths, and we noticed that the ratio was squared. Well, here it is again, because we're talking about surface area, but now we also have that additional component of cubing for volume. So it's kind of an interesting relationship. So let's dive in with some examples here. It says beach balls shown are similar with a scale factor of 7 to 6. find the surface area and volume of the smaller ball. So when we're dealing with similar figures, we're going to be setting up a lot of proportions. So what we've got here is we've got a ratio between the shapes, right? We've got 7 to 6. But we're asked to find surface area and volume for the smaller ball. So for surface area, I'm going to have to square these, and now I'm going to write a proportion. So the bigger surface area is 249.55 inches squared, and then I need to find the smaller ones. So the ratio of their surface areas should be equal to this ratio of squaring the length ratio, if that kind of makes sense. From there, you can multiply by both denominators, or you can cross multiply. I actually like to say that I multiply by both denominators, but the result is you're going to get x times 7 squared, which is 49x, and then you're going to do 36 times that, and you'll get divide the 49, and you'll get x is equal to 183.34. I don't think I rounded that. I actually don't recall. Inches squared. So that is the area, surface area of the smaller ball. Now to calculate the volume, we can't use that same ratio. We got to cube it. So we're going to go 7 cubed over 6 cubed, and it's the same setup. It's just that now we're looking at the volume, and the volume of the bigger ball is 371.61 inches cubed, but same setup. We'll call it y instead. And then, yeah, same deal, cross multiply or multiply by both denominators, and you should get that the volume of the smaller ball is 234.02 inches cubed. Okay, on example 3, we're told that the cones are similar. They give us the volume of each of them. So they say the volume of cone A is 125 meters cubed. The volume of cone B is 512 meters cubed. It says to find the scale factor of cone A to cone B. So whenever you're finding the scale factor, that's just a linear length. So what we have to do is we have to convert this back to just lengths from volume. So they keep in mind the order here. Find the scale factor of cone A to cone B. So I'm going to write cone A's volume on top, 125 meters cubed. And cone B on the bottom, 512 meters cubed. And then from there, we need to get this back down to just linear measurements. Well, to get it back down to linear measurements, this meters cubed needs to become just meters. And the way to do that is, if it was squared, we would square root, right? But since it's cubed, we're going to cube root both of these numbers. And this may be you may not be super familiar, so I probably should have done this in the other video. But you should have a cube root button. On this calculator, it's kind of funny. If I hit math, I can find a cube root. But if you can't find the cube root button right away, most of you have a button that has an X root. Whoops, hit the wrong thing. See that X root there? So you'd hit 3, then that button, then your number. But depending on how your calculator is, it could be a little bit different. But yeah, cube root. Also, what's I noticed about some newer Texas Instrument graphing calculators, which I know a lot of you are like, why are you talking about that? I'm never going to own one of those. But a lot of them, they don't even have an X root button. They just say, hey, use fractional exponents. And it's funny because a lot of us don't learn about that until later. But yeah, so a fraction exponent of 1/3 is the same as a cube root. So if you're ever stuck and you can't find the cube root button, just use a fraction exponent and it's the same thing. All right, so when we press those buttons, we get 5/8. So the scale factor of cone A to cone B is 5/8, 5 to 8. Let's flip it over, do a few more. Two triangular prisms are similar with surface areas of 9 square feet and 25 square feet. What is the scale factor of the prism? So now we've got it in, we'll do the order that they gave it to us there. 9 feet squared, 2, 25 feet squared. So to get the scale factor, we got to bring it back to linear measurements. So in this case, we're just going to square root both of them. We'll get 3 to 5. So hopefully that makes good sense. And for example, 5, two spheres have volumes of 125 pi cubic meters and 216 pi cubic meters. What is the scale factor of the spheres? What is the ratio of the surface areas? All right, so it's kind of more of the same stuff. So 125 pi, and what was it? Cubic meters, yep, meters cubed, to 216 pi meters cubed. Well, they want the scale factor, so we're gonna have to cube root all this. But before we do that, let's divide those pi's out. They're not needed. Now, they're not needed anymore. Then do a cube root. And when you do the cube root of 125, you'll get 5. And the cube root of 216 is 6. So that right there is the scale factor. And then to find what is the ratio of the surface areas, we're going to take that and square it to get the ratio of the areas, or the surface areas. So that's the areas ratio. So hopefully this is starting to click with you. If you're dealing with area, you're going to have to square the ratio. If you're dealing with volume, you're going to have to cube it. And you may need to go forwards and backwards with that. Moving on to example 6. The volumes of two similar square pyramids are 8 feet cubed and 27 feet cubed. What is the ratio of the surface area of the smaller pyramid to the larger? All right, same. Yeah, this is the same stuff over and over again. So 8 feet cubed over 27 feet cubed. And they want to know what is the ratio of the area. So let's get this back to linear. So we'll cube root it to get back to linear. But then to get the areas, we're going to have to square it. So yep, 4 to 9. And finally, I think we get to do some more solving stuff on example 7. Two solids are similar. Find the surface area and volume of solid 2. All right. Well, class, this one's got, this one's a little more interesting, isn't it? So, first things first, we are missing some lengths here, aren't we? So, on the first one, we've got a radius of 2.5, a height of 6. On the other one, we have a radius, but we're missing a height. But we're in luck. Since we're told they are similar, we can write a proportion to figure this out. So 2.5 to 5 is going to be equal to 6 to our height. I'll make that an H for a height. And I know some of you are looking at this and saying, well, 2.5 to 5, you're just doubling it. So yeah, that is a good way to do it. But there's a proportion here that you can solve as well. And we're going to get that the height is 12. So now we have some more information. I think we have enough information to do the volume component of this. So I'll go ahead and go that route. So to get the volume of this, they just want to find the surface area and volumes of solid 2. So to find the volume, we're going to need the volume of this cone. So the volume of a cone is 1/3 pi r squared h. So we've got the volume of the cone, and we're going to have everything we need for that. But in addition to that, we've got the volume of a hemisphere. So that's going to be half the volume of a a sphere. So a half times 4/3 pi r cubed. And yeah, we have everything we need to figure this out. So plug in the numbers. Radius of 5. Height of 12. Simplify that to make it 2/3. Radius of 5. And from there, we'll get 83 and 1/3 pi, 100 pi, combine them, and we'll get a volume of 183 and 1/3 pi centimeters cubed. So there's the volume. We could also multiply that pi out to get a rounded answer. But when we start to look at surface area, we're going to run into a bit of an issue. So let's take a look. To get surface area, we're going to have to get half the surface area of a sphere. So 1/2, 4 times pi r squared, no big deal. We've got the radius, so we're good for that one. But to get the lateral area, because we don't count the middle there. To get the lateral area of a cone, that's going to be pi r L, where L is the slant height, pi r L. And we don't have the slant height at the moment, but we can get it, so that's a good thing. L is this measurement right there. So what we have is we've got a right triangle. We've got legs of 5 and 12. L is the hypotenuse, so we're going to be able to solve that pretty quickly. L squared is equal to 12 squared plus 5 squared. And when you square those, add them up, and then square root, you'll get that L is 13. And now we have everything we need. And we'll get 50 pi and 65 pi. And I get 115 pi, and that would be centimeters squared. All right, well, class, thanks for watching, and your homework's on Canvas.